Hey everybody, welcome to another episode of EEs Talk Tech. My name is Mike Hoffman, and with me as always...
I'm Daniel Bogdanoff, and today we have Lee Barford. And Lee is a quantum computing expert here at Keysight. So today, Mike and I really know nothing about quantum computing, so we're very, very excited to have Lee on here. We're going to talk about what is quantum computing. Lee is in beautiful Reno, but he will also be floating somewhere over there. So we have him on the phone today. So Lee, thank you for being here. Can you tell us a little bit about yourself?
Sure. First of all, I'd like to say I consider myself very much a quantum computing beginner. I've been learning about it and helping guide some parts of Keysight into this business, into Keysight helping the real experts make some advances in quantum computing. My background is actually in computer science, despite the name of your podcast. I have a bachelor's in computer science from Temple University in Philadelphia and a master's and PhD in computer science from Cornell. However, during the 30 years that I've been with Keysight and its two predecessor companies, almost all that time I've been involved in coming up with novel kinds of software that support other kinds of engineers. Most of that time, certainly all the Keysight time, has been in software modeling techniques, simulation techniques for EEs. Okay. But during, for example, part of my HP Labs time, I was involved in new kinds of software to help mechanical engineers and manufacturing engineers.
Interesting.
Yeah. I got involved in quantum computing, and this sort of goes into what some of the importance of it of quantum computing is likely to be going forward. To back up for what's the motivation for it? As you may have noticed, clock rates in CPUs in all kinds of digital processors stopped going up in about 2006. And that was because of heating limits that were brought about. It was no longer, at that point, it was no longer possible to increase the clock rates and maintain any sort of reasonable thermal power dissipation. So the processor manufacturers, and I'm getting back to quantum computing from this, the processor manufacturers realized that they had to have more parallelism. And in fact, since about 2006, 2007, up until about a year or two ago, most of my work for Keysight involved taking advantage of that parallelism. And teaching and enabling Keysight engineers to improve our product performance by taking advantage of the parallelism rather than the clock speed available in microprocessors for the last decade. Microprocessors, GPUs, FPGAs.
I remember that. I interned for a chipset manufacturer in high school right at that 2005, 2006 range. And I did a lot of benchmark testing in the lab, and it was right when multi-core processors were starting to get popular. Yep. And all we did was benchmarking, and it was, you could tell certain softwares were taking advantage of the parallel processing, and some were basically just using one core because it's kind of a symbiosis. You have the hardware, but you have to program for that hardware. It's not done automatically.
Interesting. Right. That makes sense.
And then there are additional features, such as most processors now have vector instructions that can do multiple integer floating point operations per cycle. If you have or per instruction, if you have multiple operations ganged up in a single register, there's the use of graphics processors as basically vector and matrix machines that can accelerate all sorts of signal processing and matrix math in addition to the graphics for which they were originally intended. Now,
Thank you, video games.
Yes, thank you, video games, but also thank you, physicists that went to the graphics chip companies and said, "Look, we can do this neat stuff with your chip. Please open up the interfaces so that we can do that." And the graphics chip companies saw a market there and complied, and provided,
like Bitcoin mining. I think they use graphic cards for that kind of stuff, right? This kind of blockchain style calculations, because they're so much faster in some cases with a video card.
So the physics, heavy use in physics, heavy use for all kinds of simulation, including electronics, including electronic simulation, heavy use in biotech. Also, well suited for all those things. As I might mention later when we come back to it, they're also very good on the sorts of computation you need to simulate quantum computers, which is an important thing. Because they're quite expensive to build, and there's a lot of the experimentation that's happening is with simulating them, including simulating them with the assistance of GPUs, so you can simulate bigger ones. And why that's interesting, I'll get back to. Anyway, we're going down the path of having more and more parallel computers with every tick-tock of the cycles of improvement, including feature size shrink in semiconductors. However, when we get down to right now, depending on who you believe, there are parts out there being made at 10, maybe 7 nanometers. None of the manufacturers are very specific about what that actually means. But let's say that actually means that there's an actual feature size in the digital transistor that's, say, 7 nanometers today. That means in not too many more years, we'll be heading below 5 nanometers. And at that point, there aren't very many unit cells of silicon left. A unit cell of silicon is about half a nanometer. So at 5 nanometers, we're down to about 5 unit cells. I don't know what that is, 35, 40 atoms, something like that, of silicon, and then you've got the dopant atoms in there. At that point, you've got few enough atoms that you're close to or at the point where quantum mechanical effects are going to disturb the electronics. So one way...
So when you say quantum mechanical effects, is that like the uncertainty principle?
It's like the uncertainty principle. It's like... It's like the uncertainty principle. It's like the fact that when you measure the physical state, that the act of measurement itself will noticeably perturb the state, including taking it from an indefinite superimposed quantum state, a la Schrodinger's cat, to a definite state. It means having superposition of states. Well, I mentioned Schrodinger's cat already, right? That's the superposition of the states: the cat alive, the cat dead. In digital electronics, that would be a 0 state and a 1 state, and you have some probability of being in one or the other. And the act of actually measuring the bit, so that you can do some other computation with it, or so you can read it out, will force it definitely into the 0 or 1 state, even though it was formerly in one or the other. And also just the noise the noise and disturbances that come from the physical roughness at that kind of level, and the fact that manufacturing errors that are relatively small will mean you have a different number of atoms in each replication of that transistor, say. But you don't have that very many transistors to start with, right? So you're going to have higher and higher manufacturing variance, just because normal tolerance of a couple atoms one way or the other is a big difference in the number of atoms in that transistor.
Yeah. Your tolerances get quantized into
exactly.
That's unreal.
And even though a physicist wouldn't call that a quantum mechanical effect in the theoretical sense, as you notice, it still has to do. It's still coming. It's coming from the fact that you're dealing with quanta. You're dealing with individual atoms, and the count, even the count of them, starts to matter. So one way to talk about quantum computing is that it's just one way of moving the computer industry past that barrier. There are others out there. There are other approaches, and I'm even less expert in them, and so I won't go there. People can Google for them for how to get past that barrier. One way to look at the quantum computing and the reason for their investments in quantum computing is it is one of the potential ways past that barrier.
Basically, is that the barrier, Moore's law, essentially reaching the limits of physics?
Moore's law reaches the limits of physics, and so there's kind of two things you can do. On the one hand, you can try workarounds and error correction methods and computational approaches that can deal with high error rates in the fundamental electronic operations, and do sorts of error correction mechanisms that deal with the fact that the underlying digital electronics are going to be very noisy. But another approach is to learn to engineer with quantum mechanical effects and take advantage of them.
So you're at a party, and someone comes up to you and says, "Lee, I've never heard of quantum computing before. What is it?"
What is it?
Sit down, grab a drink.
It's
how much time do you got?
It's the use of it's taking advantage of it's taking advantage of quantum mechanical effects, engineering with them to build a new kind of computers that for certain problems promise but are not proven to do better than what we have now, even what we could build at when we get to the end of Moore's law.
Okay. Yeah, will we? Do you think we will?
I don't know.
Get to the end of Moore's law?
Will we see the end of Moore's law? It depends on how you define Moore's law. If you define Moore's law to mean that digital CMOS shrinks every 18 months, or now it's somewhat longer than that, which in itself is a sign of the potential end. Yes, Moore's law has to end, because you can only make transistor features so small. If, on the other hand, you use Moore's law to colloquially mean electronics continues to advance, so that there's more computational capability, faster, wider bandwidth, analog capability, the ability to build larger parts at less cost, I don't see that that's coming to an end, because there are lots of different experimental approaches to move forward after and by experimental I mean being researched at universities around the world, for moving beyond the end of digital CMOS as we have known it, and continuing to allow the electronics industry to make progress. So all of those approaches would need to fail. Right. In order for progress in electronics to stop, all those experimental approaches would need to fail, and they're not all going to fail. Some of them will succeed.
Right. So I guess the answer is if you want Moore's law to fail, you can define it as such that it will definitely fail, and if you're a Moore's law fanboy, then it will continue to live on.
Well, I mean, you can think back to the old days of vacuum tubes, right? And it's like those could only get so small,
right?
And then it's like, boom, now we have transistors, and you could kind of say Moore's law is independent of the technology being used. I think that's
yeah.
If
I know there's some Moore's law haters out there.
Again, though, I want to draw this distinction. Strictly speaking, Moore meant his law to apply to large-scale integration, he would have called it. back in the early '60s, right? And so if you're being formal, right, that's the real meaning of Moore's law. If you're being informal, Moore's law just meaning electronics gets faster, cheaper, better, then you're right.
Okay. Awesome. So, we're actually nearing-ish the end of what we normally consider to be an episode.
Okay.
Do you want to take if we had a few minutes left, is there anything else you'd like to discuss? We talked about, technologies and challenges leading up to quantum computing. Can you give us a little bit of teaser for future episodes? Because we'll definitely have you on another.
Yeah, sure. I think future episodes can cover things like what sorts of technology goes into a quantum computer, what the current state of experimentation is. What are some more of the motivations, including where the money is coming from? And I think we probably also want to say, how is Keysight already involved in helping those experimentals make progress?
Because we've you were saying before we started, we've been secretly-ish involved in quantum computing up to now, and you've kind of had to redact your resume or more or less, and this is a bit of a coming out for us.
Sure.
That hey, we are here.
I'd be interested in too knowing what kind of problems quantum computing is trying to solve, and will quantum computing, as we know it today, morph its way into consumer electronics to replace the CMOS-based computing we have today, or is it purely a specialist, super high-end application for the
near
future?
And that's a question I can probably talk about, but absolutely not give you a definitive answer, because one of the things we'll be talking about
computing
is that right now pretty much most quantum computing experimental approaches require very extreme environments, very high vacuums or very cold temperatures that you and it's hard to see how those approaches are going to be in consumer products.
Yeah.
Okay. In the last couple minutes we have left, you talked about how we have to, quantum computing is about using those quantum effects. I'm going to use the term loosely, quantum effects, to our advantage. Can you give us a brief overview of what that is?
Sure.
Not necessarily specifics of how people are doing it, but what does it look like?
So I think that the simplest one to describe is that of superposition of states. As a consider. I haven't used any of the terminology yet, but in quantum computing, the fundamental storage unit is something called a quantum bit. And in a quantum bit, a quantum bit can be in states that are superpositions or mixtures of 1 and 0. If you have a quantum register consisting of, so that's analogous to the Schrödinger cat, right? It's alive or dead with some probability. Likewise, a quantum bit can be a 1 or 0 with some probability.
That doesn't seem useful to me. That seems like counterproductive.
But what happens if you have a quantum register of n bits and you want to store a number of n-bit data? You can store them all. You could store them all with, if you want to make them indifferentiated, you can store them all with equal probability.
Interesting.
And then there could be an algorithm for searching all of those. And there is such an algorithm.
Can you give us a simple example? So, like, you have a 10-bit register and you need to store 10 bits.
You could store a number of different 10-bit numbers in the same register and compute on them.
Assuming 10 factorial ones, right?
Yeah. or
Yeah,
2 to the
I'm still trying to wrap my mind
or
around that.
potentially, assuming that you had incredibly accurate
2 to the 10.
physical, right? Assuming you had a sufficiently accurate quantum bits, sufficiently no noise quantum bits, you could store all the 2 to the 10th possible 10-bit numbers in that register. Usually, it's going to be more interesting.
How do you read them?
That's one of the tricks. You can only the bad news is you can only read one.
You can only store them.
You can store them all,
Okay.
but you can
Okay.
if you have them all stored with equal probability. One model of quantum computation is just like when you open the box and Schrödinger's cat is either alive or dead once you look inside. Once you read that register, you're only going to get one of the answers. And
even if you reread the register a second time, it's going to be identical
because
to the
just
first
like
time?
Schrödinger's cat, it will collapse to being live or dead. Right, Schrödinger's cat, you close the box and open it again. If the first time you looked at it, the cat was dead, it's still dead when you look at it the second time.
So
it's the same thing with that register. When you read it the second time, it's going to be whatever value you read the first time.
So how do you get what you want out of it?
The answer is
because, like, theoretically, you're trying to.
Sure, you're going to do as much of the computations as you can with the computer operating in the undisturbed, unread mode, and then only when the algorithm requires it or it's finished do you read it and get an answer.
So you can basically like reduce out your formulas and your computations until it depends on what that is specifically.
Yeah.
And then you read it out and you're like, oh, okay, that's it. Here's our answer.
That's one way it works. Now, typically, the answer is typically the algorithms are random algorithms. So you were expecting to get that have you have the following properties. Either the algorithm is going to give you the right answer with such high probability that you don't need to check it, or the problem was one that it's easy to check that you got the right answer. So one of the problems that people are very interested in is factoring very large numbers, because that can be important in cryptography.
Yeah. Security.
Breaking RSA is the 2-word explanation.
Okay, so it kills me to cut us off.
But we have okay.
End the episode here, and we will definitely be picking this up. Maybe we start back up talking about security next time.
Yep.
And, we may even, instead of every other week, do some. Depending on how long we're here chatting, do a weekly thing instead of every other week thing. So thank you, Lee Barford. That was fantastic.
My brain is melting.
Make sure you subscribe to the EEs Talk Tech podcast or the Keysight Oscilloscopes YouTube channel. You guys know the drill. If you're on iTunes or Google Play or Stitcher, or any of those, the podcast is there. Please give us a rating. Give us a thumbs up if you like this video, and subscribe to the Keysight Oscilloscopes YouTube channel. Daniel Bogdanoff, Mike Hoffman, Lee Barford. We will see you next time.
Thanks.
Cheers.